finishing my PhD in the math department here in Oxford. So I do research in string theory, but today I want to tell you about Einstein's theory of general relativity and some cool consequence of his model that is all around us in our universe. And towards the end, maybe we'll get towards some topics closer to my actual research. So let's get started. Sorry, my slides are not passing. Okay, there. So Einstein's theory of general relativity is a theory of gravity. So gravity is our starting point. So when you think about gravity, maybe you think about the effects that attracts us towards the Earth, and that makes a ball fall, an apple fall. And Newton wrote a law that describes this attraction. That is just that the force is equal to the mass times the Earth, the acceleration of the Earth, this little g. And actually, Newton's great insight was to think that this force acting on you and on Apple is actually the same force that acts on planets and keeps them in orbit around the sun. And so it wrote this general law of gravitation that is just that the force between two masses, the product of these two masses divided by their distance squared and multiplied by this capital G, which is the Newton constant. And so now if you just set one of the mass to be the mass of the Earth and the distance to be the radius of the Earth, you reobtain the formula from the previous slide as a special case of the gravitational force on Earth. But with this general law, you're actually able to describe the movements of basically everything in our universe. And so in particular, this predicts that the planets have this elliptic orbit around the sun, which was something that had been observed for some decades already at Newton's time, but no one was able to explain this phenomena. And then Newton wrote that equation, and that described the movement of planets properly and everything else that people were observing, really. And so this law went on for centuries. People used it for everything. That was even enough to send the first man to the moon. So really a powerful law. And so no one was really questioning it. That was just a good way of describing gravity until Einstein came along in 1915 and completely revolutionized the way to think about gravity. So he has this amusing quote saying, "I have no special talent. I'm only passionately curious." So basically didn't see himself as anyone special in that sense. But he did have one talent, too, which is exactly his curiosity he mentioned. And so he never took anything for granted and was always challenging even the best established models such as Newton's law, and that's how he made such revolutionary progress. And so in the case of gravity, his great insight was to actually start from Newton's idea. So Newton's first law tells you that if you don't touch an object, it keeps moving in a straight line. And Einstein's idea was to say, well, but what if that's still true when gravity is present? So what does that mean? Einstein's idea was that objects move in straight lines, but in curved space, and gravity is actually the curvature of space-time. When the mass is present, space-time gets curved, and objects then follow straight lines in that curved space. So what's called straight line in curved space? So if you think of yourself walking on the surface of the Earth, you feel like you're going straight, but you're actually describing circles. So these are straight lines on a curved space, and that's the trajectories that object takes in the presence of gravity from Einstein's perspective. And so he formalized his idea into one beautiful formula, Einstein's equation, which is basically the only formula you're going to see today. Was too beautiful to not write down. So on one side, you have this object that describes the space-time geometry, and he equates it on the other side to the matter contents of space-time. And so this equation has been summarized in this quote by Wheeler that says, space-time tells matter how to move, and matter tells spacetimes how to curve. So really how the left and right-hand sides of this equation communicate with each other. Geometry is equal to matter. And one thing you can see also in that equation is this G is the Newton constant again. So same constant as for Newton. And now we also have the speed of light appearing. So it looks like an innocent equation that's just three terms and not that impressive, but that's actually really difficult. And there is a lot hidden in that equation. That's so difficult to solve that when Einstein wrote it down, it actually said that no one would ever be able to solve it beyond just the trivial case of flat space-time, no matter if everything's flat. He said that would be the only solution we would be able to write down. But only 1 year after, there was this guy, Schwarzschild, was a German soldier. He was fighting in the trenches in the First World War, and I already got a bit bored there because he decided I would rather try and solve Einstein's equation. And he actually managed to find a solution to Einstein's equations, and not just a solution. He actually wrote down the solution that describes space-time around any spherical mass. So he wrote the geometry of space-time around any sphere. Might it be an apple, the Earth, the sun, or as we're going to see later, a black hole. So using Schwarzschild's solution, we can actually describe all the effects I'm going to be mentioning for the rest of that presentation. So quite a good solution to Einstein's equation. But this equation is so difficult, as I was mentioning, that people are actually still looking for solutions. So that is still an open question in theoretical physics to come up with more solutions to Einstein equation. But that's an active area of research, and now people are even using AI to try to find these solutions. So let's summarize what we have so far. So from Newton's perspective, gravity is a force acting between two objects, and then Einstein came and gave a completely different perspective on gravity. There's no force left, so gravity is not a force anymore. That's really the space-time curvature and objects moving in space-time, in this curved space-time, sorry. But, okay, that's very different in conceptually, but on a daily basis, we said that was perfectly fine to use Newton. So why would we bother with Einstein in some sense? So Newton was working really well. Now I'd give you a different perspective. It looks nice, but the equations are really difficult to solve. So why do we want to use Einstein instead? Well, we're going to see some experimental difference between the two models, but before getting there, let's just do one thought experiment. So what do you think would happen if the sun were to disappear both from Newton's perspective and from Einstein's perspective? I'll give you a few seconds to think about it. Okay, let's look at Newton first. So if I get rid of the sun, what happens for us is that one of the two masses in this gravitational law disappears. So now I just have zero force acting on me on the Earth, and so the Earth just gets ejected out of its orbit. And in particular, one key point of that effect is that it happens immediately. No sun, we get ejected. Okay, so now what happens from Einstein's perspective? So the sun disappears, poof, and now it takes some time for the information to get to us, but once the information gets to us, I mean, same thing happens, we get ejected out of our orbit. So obviously this video is way too fast. That wouldn't take 3 turns of the Earth around the sun, so 3 years for that to happen. But actually we can know how long that would take to happen. And it would actually take 8 minutes for this information to get to us. And so what's the idea between these times? The sun is situated 150 million of kilometers away from the Earth, and then the time that it takes for the information to get to us is this distance multiplied by the speed of the information. And the information actually propagates at the speed of light, which is really fast. So it takes 8 minutes for it to come to us. And the fact that we get the information at the speed of light is related to Einstein's other theory, which is the theory of special relativity, which unfortunately we don't really have time to discuss today, but really the assumption that is that's at the origin of the theory of special relativity is that nothing travels faster than light. And so then you get various consequences. One of them is the famous formula E is equal to mc squared. So that's a consequence of this postulate that nothing travels faster than light, which is in particular violated by Newton's theory. So before, when the sun disappeared, we knew about it immediately, even though the sun is far away. So the information was reaching out faster than light. So Newton's theory is incompatible with Einstein's theory of special relativity. So we're going to leave special relativity on the side for a bit now, but we'll come back to that towards the end. So this was just a third experiment. The sun didn't have never disappeared, so that's not a good test of general relativity, but we can actually also get experimental proofs of general relativity. So we mentioned on daily basis, surface of the Earth, you don't see much of it, but if you go instead to some astronomical setup, you're going to see some proof of it. And the first one that historically was related to the orbit of Mercury. So it had been a few decades, middle of the 19th century, people observed that when Mercury was going around its orbit, on the next turn of the orbit, it didn't take the exact same ellipse, but rather a slightly shifted one, which is called precession, the precession of the orbit, sorry. And people couldn't really understand why this orbit was precessing, because if you just take Newton's gravity, Mercury keeps going around that ellipse. And so people were conjecturing that maybe there was another planet actually between Mercury and the sun that would actually cause this shift. But then they were trying to observe that planet and they couldn't see anything. So that wasn't working too well. And then Einstein wrote his theory of general relativity and doing the computation of the orbit of Mercury using general relativity instead of Newton's law. What you find is that the orbit of Mercury has a slight shift every time. You can compute even the value of that shift, and you find that this shifts of 43 arcseconds per century. So it is a tiny, tiny effect, but it matches exactly the shift that was observed for this since a few years and was trying to be matched. So that was a perfect prediction of general relativity, completely confirming and explaining observations. So that was the first historical proof. People were really happy about it, but still Einstein's theory is quite difficult. So we need more proofs to get everyone on board. So there is a second experiment that's really convinced more people, and that's the one I want to describe now. So we said that objects follow straight lines in curved space. Well, that also applies to light. So imagine I have some star emitting some light, and this light gets to the Earth. But if some massive object is in the middle of the star and the Earth, so for example, the sun, then space-time gets bent around the sun. And so the trajectory of the light coming from the star gets deviated when it passes close to the sun. So rather than observing the star where it actually is, you would see it somewhere else in the sky. But the main problem to observe that effect is the sun is so bright that usually you don't see stars when you see the sun, right? So you're not really able to see the star anywhere like at a different position. The exception to that is if the moon is actually hiding the light from the sun, and that's what we called a solar eclipse. So actually, such a solar eclipse happens only 4 years after Einstein wrote his theory. And so during that solar eclipse, some measurements were done about some positions of the star, and they measured the shifts between where the star was and where it was supposed to be. And they found a perfect agreement with the prediction of general relativity for this shift. And so there, people were quite convinced that general relativity was a good model to use. So these are the two first historical proof of GR, but there is a third effect I would like to mention, and it's actually relevant for you every day. So do you know where GR appears in your day-to-day life? Okay, before giving you the answer, let me tell you which effect is involved. So we said that the presence of mass deforms space-time. So the last two examples, the space-time was deformed so space was deformed by the presence of the mass. So trajectory of the light was bent by the sun being present. So that's a spatial effect. But actually, this is the full space-time that is curved by the presence of the mass. So in particular, time is distorted, and you can actually write an equation for it. And so if I'm standing at a certain distance r of a certain mass m, and I'm holding a clock, the time that is going to pass on my clock is given by that formula. So it's a modification of some reference time. So this little t is at infinity, and the time that is passing on my clock is modified by the square root. That again depends on the mass and my distance to the mass. And so in particular, my clock runs slower when I'm closer to a mass. And the effect of that you may have seen. Don't know if you guys still watch Interstellar, but sorry if you haven't seen it, I'm going to spoil the movie. So this dad goes to a planet far away that is very massive, and then he spends some time there and then comes back to Earth, and his daughter is way older than him. Well, that's because his clock got slow while he was close to that planet. So why is it relevant for us? Well, because you need to take into account that effect in order for your GPS to work. So let me explain that. How does a GPS work? Well, I'm standing at some point on Earth. I'm sending a signal out in space towards some satellites. The satellite get my signal and send it back, and I can measure how long it took for my signal to get to the satellite and back, and I basically triangulate my position because there is only one point that is at some distance of the three satellites. Okay, but because the satellites are at a certain distance of the Earth, which is the mass, their clock is running at a different pace. And so they're going to tell me that they got my signal at a certain time, but I need to actually adapt what time their clock is showing with respect to the square root I showed you on the previous slide. And so if I wasn't adapting their clock would be shifting of 38 microsecond per day compared to mine, which seems like a tiny amount of time, except that again it's multiplied by the speed of light, which is a big number, and so that would actually lead to a shift of 10 kilometers per day in the prediction of your GPS. So after a few days, your GPS would be completely unusable without GR. And so GR is important for GPS, but the theoretical physicists particularly like that example because we keep being asked basically what our research is useful for. Well, you have no application. And so our answer to that criticism is often to say, well, Einstein didn't know his theory would be used for GPS a century later. So we're basically waiting for someone in a century to find an application of our research. So you can use that excuse next time. All right, let's get back to GR. So we saw that light gets bent when it passes close to some mass, and that also time slows down. But see, what is the most extreme effect I can think of? Yeah, we're going to talk about black holes. So black holes typically arise when a star collapses into itself. So I start with a star, and then it just collapses, and all the mass of the star gets concentrated in a tiny region of space, and then the gravity is so high in that region of space that actually light can't escape anymore, and time slows down so much that it virtually stops, and that's what we call a black hole. And the line basically where that happens, this point of non-return, is called the event horizon. So anything that passes the event horizon of a black hole can't ever escape again, including light, and that's why we call it black. So it's a beautiful and mysterious object, and actually it was already predicted theoretically from basically the start of GR. So when Schwarzschild wrote his solution, he noticed that he was able to write down at which radius this event horizon like appeared. So like if you look at Schwarzschild solution, there is a radius that where something weird happened, and you can't basically come back from, and that's what we called the event horizon, and that's just proportional to the mass. And that actually tells you how dense a black hole is. So if all the mass is concentrated in a region that is smaller than the event horizon, that's what we call a black hole. And so for example, if I take the mass of the sun, and then the Schwarzschild radius, the event horizon, is of 3 kilometers. So that's what I'm drawing on that map here. I'm basically saying that if I'm able to compact to put all the mass of the sun within Oxford, that would give me a black hole, and the light wouldn't be able to escape. So that's very, very, very dense. So another example, if I take the mass of the Earth instead, this radius would be the one of a marble. So I really need a region of space-time with an extremely large density. So this is just the theoretical prediction, but it actually took another century in order to actually observe these black holes experimentally. And so in 2019, got the first ever image of a black hole, which was the one of M87. And it's actually really beautiful how this image was obtained, because if you just point a telescope at a black hole, well, you don't see anything, it's black. So what this image really is that there were telescopes all around the globe taking data, all pointing towards that black hole. And on each individual telescope, you wouldn't see a thing. But then by combining the data from all these telescopes, you were able to generate the image that you see here. And actually also what you see on the image, so the black hole is really the black region. And so the orange thing that you see is actually the matter that orbits the black hole. So that doesn't fall in, that just orbits around the black hole, and the gravitation pull is so strong that the matter is very excited, and so it emits some radiation, and that's this radiation that you observe on this image. And 3 years later, they took another picture of another black hole, Sagittarius A, that is the one center of our galaxy, and people knew that there was this black hole there and some of their properties, because it had already actually been studied in an indirect way, so not taking a pictures, but actually looking at orbits of some objects in our galaxy. So this is data taken over 20 years. And basically what people noticed is that a bunch of objects seemed to be orbiting something, but then when they were looking, they didn't see anything. And so they said, oh, maybe it's a black hole that is being orbited. And so a team of people actually reconstructed these orbits entirely and computed the properties of this black hole, Sagittarius A, and for their observations, they got the Nobel Prize back in 2020. And I want to mention that this Nobel Prize was actually shared between this experimental discovery together with a theoretical part for theoretical discoveries about black hole, and this part was awarded to Roger Penrose, who has his office just down the corridor. So that's pretty cool. All right, so we saw two ways of detecting black holes, either through pictures or through these orbits. But there is a third way you can detect black holes, and it's through gravitational waves. So we've talked about planets orbiting the sun, and now stars orbiting black holes on the previous slide. But you can also have black holes orbiting black holes, and that is a very extreme gravitational phenomena that actually creates gravitational waves. So gravitational waves are actually coming out of Einstein's equation. That's one of the prediction of the equation. So if you write the Einstein's equation for a system of two black holes, here is the computer simulation of what would happen. So it's really difficult to solve on a piece of paper, but the computer can solve it for you, and that's what would happen. So basically, when the black hole moves through space-time, it actually kind of drags space-time with it, creating that wave. The same way if you were to drag your hands through water, you would create a wave. Well, black holes are very massive, and so that's what happens. And in particular, so the two black holes are orbiting each other, and the wave carries some energy away from the system. So some energy is dissipated in the wave. And so because this system is losing energy, it's going to start orbiting closer. But because it's getting closer, to conserve angular momentum, it's going to start orbiting faster. But then it's going to emit more energy in the wave. So it's going to get closer, so it's going to get faster, so it's going to emit more. And that is actually this accelerated spiraling process that's happening until eventually the two black holes merge into a single object, and that marks the end of the event. So again, coming out of Einstein equation really quite easily, at least in principle. And so when Einstein wrote down this equation, it basically said, well, there are like three ways of testing my theory: the orbit of Mercury, the solar eclipse with the shift of the star, and the existence of gravitational wave. And whereas the first two proofs had been tested within 5 years after he wrote the model, it actually took 100 years to test the gravitational wave experimentally. And so now I want to describe how this experience works. So in order to detect gravitational waves, I actually need to introduce another wave that is the one from a laser. So the experimental setup that is used is called an interferometer. So the way it works is that I send a laser beam, and this beam is split in two directions. It's going to go along these two arms, and at the end of the arms, it's being reflected by some mirrors, and so it comes back. And when it comes back, it's being recombined, and then I observe the recombined signal on the screen. But the point is that depending on the phase of the two waves coming from the two directions, when they meet again, I'm going to observe a different signal on the screen. So if the two waves are in phase, then their amplitudes add up, and I observe a large amplitude on the screen. But on the other hand, if they're not in phase, then their amplitudes cancel each other, and I observe nothing on the screen. And whether or not they're in phase depends on the relative length between the two arms of my interferometer. So in particular, if I have a gravitational wave passing through my interferometer, it's going to change the length of my arms, and so I'm going to observe a different interference pattern coming in and out of my screen. And so that's actually what had been detected in 2017, a gravitational wave passed through the Earth. So in particular, it also passed through you. Well, you didn't notice because it's a very tiny effect. And it passed through these two interferometers, one in Washington and one in Louisiana. And they observed this interference pattern on the screen and translated it into the passage of a gravitational wave. And they actually observed the exact same signal. This one just happened slightly after, just the time that the wave got from Washington to Louisiana, which happens quite fast because gravitational waves travel at the speed of light. But they observed the same event, and their observation also matched with what was predicted theoretically within Einstein's equation. So a good proof of general relativity. And they got a Nobel Prize for that. So a lot of Nobel Prize in this area, in case you're interested in doing research there, may get a chance. Also, they're thinking of sending another of this interferometer into space, so it could be a lot larger and detect a lot more of these gravitational waves events. And they're thinking of launching it in 2035, so there should be plenty of gravitational waves data by the time you get to your PhD. So yeah, feel free to ask questions before I get to the next part. Otherwise, I'll take questions at the end anyway. But if you want to just take a little break for a question now, we can as well. All right. Well, then I'll tell you about another thing that here general relativity predicts, which is what happens to our universe. So, as you may know, general relativity predicts that the universe is in expansion, and in particular, if you run that argument backwards, that it came from a single point in space-time that we call the Big Bang. So the universe started at the Big Bang and now is expanding. And that actually comes out of Einstein equation. So I'm writing it again. And actually, I'm adding a term compared to the version that you saw on the first slide. So on the first slide, there was only these terms. And now I'm adding this one with this red lambda that is called the cosmological constant. And that's actually the value of this parameter lambda that dictates the rate of the expansion of the universe. And there is actually a fun historical story around it. So when Einstein wrote his equation for the first time, he didn't put that term in. So he wrote the version I showed you at the start. And what I noticed is that without this term, actually, if you start with a static universe, then the universe would collapse on itself on the under its own gravitational pull. And Einstein didn't like that. I was like, no, the universe not moving. Start with a static universe. I should keep a static universe. So he actually found that if he added this term in, it was able to keep the universe static. And that's exactly what they wanted. They said, oh, the universe neither contracting nor expanding. And so it sets the value of the cosmological constant in order to have a static universe. But it didn't like it too much. It didn't think that was a very elegant solution, but it was quite convinced the universe was static. And then a few years after that, Hubble came in and did some observation and said, hey guys, actually the universe is expanding, but that's fine. General relativity is happy with it. You just need to take another value for the cosmological constant. And if you tune the cosmological constant differently, then the universe is actually expanding in Einstein theory. And so Einstein could have predicted the expansion of the universe, but actually didn't. And that's he refers to this mistake as his biggest blunder. So even Einstein makes mistake, and he completely missed on the expansion of the universe. But eventually everything works out with these cosmological constants. So depending on the value of this cosmological constant, the universe expands at a different rate. And so there are different scenarios depending on the rate of acceleration. So on one hand, if we're expanding in a very accelerated way, there is a quite violent scenario that can happen. It's called the Big Rip, where everything gets torn apart. So every atom gets separated and everything gets torn. That's called the Big Rip. Then if we accelerate more steadily, basically things keep getting apart and apart and apart. And eventually that leads to the temperature being very low. That's why we call the big freeze. So yeah, everything just gets frozen. And the last scenario is that the acceleration, we actually kind of stop expanding. So the acceleration stops, and instead we start crumbling back on ourselves. And so that's the scenario. It's called the big crunch. So the universe just falls back to a single point. And actually this scenario is quite interesting because then you could imagine that from this single point you have another Big Bang. And so that's one of the theory of what happens before the Big Bang, is that actually there was another universe that crunched, and then we're back at the Big Bang and so on. And there is this cyclic life of the universe. And so this is known as the Big Bounce. And that's also one of the possible cosmological model. And in particular, with our current measurement of the cosmological constant, we're not able to distinguish between these scenarios. So basically, our measurement of the cosmological constant could tell us on which line we are. But as you see, for the present time, these lines are really close to each other. So you really need a very precise measurement to decide which scenario is happening. And at the moment, we're too uncertain. We do think that the big freeze may be a bit more probable, though. So actually, we want a better measurement of this cosmological constant, and that's why we sent the James Webb Telescope in space a few years ago to try to measure this cosmological constant, also called Hubble constant, more precisely, and get a better sense of what's happening for our universe. So let's summarize a bit what relativity explains or does not explain. So it does predict that the universe is in expansion, depending on the value of the cosmological constant, but it doesn't tell you what drives this expansion. So it's expanding, but why is it expanding is not incorporated in relativity. And so there are some cosmological models trying to explain what pushes the universe apart, basically, and that relates on the presence of what's called dark energy. And so if you include dark energy in the universe, then the universe is expanding, but we actually don't know what dark energy is. We know that it should be present, it explains the expansion, but what it is, we don't know. That's why I call it dark. But we know there should be a lot of it, but we don't know what it is. So another thing that is not really predicted by general relativity, so we can measure the value of the cosmological constant. So general relativity incorporates this cosmological constant, but it doesn't give it a value. It just says that it's somewhere in the formula, and then you do observations, and you can deduce the value of the cosmological constant. And what we observe at the moment is that it's a very, very, very small value. It's not zero, but it's very small. And general relativity has no reason why it should be non-zero, but small. And so this question is known as the cosmological constant problem. And people in cosmology are actively trying to find reasons for that. Another thing I want to mention on that diagram is this dark matter sector. So what happens is that in certain regions of our universe, when we observe there, we see that there is some gravitational pull happening. But at the same time, we don't see any matter creating it. And so to account for this gravitational thing happening, we include the presence of dark matter there. But again, we have no clue what it's actually made of. So in summary, we understand about 5% of the total content of the universe. So there is a lot of open question and work to do in cosmology, and that's a very active area of research. So there are two other things that are predicted by general relativity. So the existence of black hole and the existence of the Big Bang. But even here, there are some parts that are not fully explained by general relativity. So general relativity predicts that there are these regions of space-time where nothing can escape from, and the event horizon part is well understood. But what's not understood is what happens exactly at the center of the black hole. So if you keep zooming in, what actually happens at what we call the singularity. So the singularity is really the center of the black hole. And there, the mass is so dense that basically the curvature of space-time becomes infinite, and the equation of general relativity breaks down. So general relativity is not able to describe really the interior of the black hole. And similarly, if you go back in time all the way to the Big Bang, then you also get this tiny, very dense region. And again, general relativity breaks down. So you are actually not able to describe the first second after the Big Bang using general relativity. And what you need is actually another theory of quantum gravity. And this theory is actually not known, but if you want to talk about black holes or the Big Bang, then you need to actually include quantum effects within general relativity. And at the moment, we don't really know how to do that, but we have some candidates for it. And so that's what I want to talk about now. And in particular, I want to tell you a bit about the quantum part of quantum gravity. So what do we call quantum, and what are quantum effects? So let's talk about some experiments. So imagine I throw some tennis balls to a wall with two slits. So the tennis ball will go through one slit or the other, and then if I place a screen on the other side, I can measure basically if the ball went through one slit or the other. So that's what I meant. That's what I would observe on my screen. Now imagine that I repeat the same experiment, but rather than throwing tennis balls, I throw some lights. So what would happen is that light is a wave. So I have my wave getting to the wall, and it splits between the two slits. So now I have one wave going through each of the slits, and then I have two waves on the other side that interfere with each other. And so that's the same diagram as I was showing to detect gravitational waves. Depending on the two phases of the waves, they're going to interfere constructively or destructively, and I get some interference pattern on the screen. So what I get on the screen is quite different if I throw some balls or if I throw a wave through my slits. Okay, so now the interesting question is, what happens if I throw electrons through that slits? So intuitively, you'd think that electrons are little particles, so that they're basically tennis balls, and I will go through one slit or the other, and I would obtain that pattern on the screen, right? Well, actually, if you run the experiments, what you would observe is that after the electrons been thrown through the slits, that's the pattern that you get on the screen, the pattern that you get when you send a wave. So basically, that means that the electrons went through through both slits and interfere with itself and created that interference pattern on the screen. So the electron's not a particle, it's actually a wave. So that's a very peculiar behavior. So the electron's a wave, but now it gets even weirder, because if I'm now trying to observe the electron going through both slits, so now I place a detector and I'm trying to see the electron doing its business going through the slits. Now the electron's going to behave like the tennis balls. What I would observe on the screen is this pattern of the electron having passed through one slit or the other. So an observed electron is actually a ball. So that's a particle. So this effect is referred to as the wave-particle duality. So a non-observed electron is wave, and then an observed electron is a particle. And there is a thought experiment that had been designed by Schrödinger to talk about that effect. So basically, the electron going through both slits is in a superposition of states. So it goes through both slits at the same time. And so Schrödinger designed this thought experiment of putting a cat in a box with some, again, that is just a thought experiment. No one put the cat in the box for real. And you put a bottle of poison with it, and there is this source of radioactivity that can emit a radioactive particle that would release a hammer that would break the poison, that would kill the cat. And so from a classical perspective, that means that the cat is either alive if the poison has not been broken, or dead if the poison has been broken. And what Schrödinger suggested is that actually from the quantum perspective, as long as the box is closed, the cat is both dead and alive, is in the superposition of states as the electron is passing through both slits at the same time. And then once you open the box, you observe, and that makes the cat being either dead or alive, the same way that now the electron is passing through either one of the slits, just as the tennis ball. And so this effect of the observation making you pick a state is known as the collapse of the wave function. So the way I can think about it is that before observing the electron has a certain probability of being at any position in space, basically, and passing through both of the slices, behaving like this wave. But then once I observe the electron, it actually picks a slit. So it actually gets localized to a specific position. So its probability collapses. But even here, you see that there is still a little wiggle room of where the electron can be. And so there is still some uncertainty on its position. And that's actually really important. And that's called the uncertainty principle, that tells me that I can't measure the position of the electron. I can only measure it up to a certain precision. And this precision is actually related to the uncertainty I have on its velocity. So the way to think about it is, what does that mean to measure very precisely where the electron is? So the action of measuring is actually throwing photons to my electron, and then the photons bounce back to me and give me the information of where the electron is. But if I want to know the position more accurately, I need to basically throw more photons on the electron. But by doing that, I'm basically bothering the electron and making it kind of move around. And so I'm giving it some momentum. And so the more I'm trying to get precision at the position, the least precision I have on its momentum. On the other hand, if I give it a precise momentum, then I can't know the position very precisely. So, and the bound on this is given by this h bar. That is the reduced Planck constant, which is really the scale at which quantum mechanics happens. So that's a very tiny number. And so, for example, you are also subject to this uncertainty principle. So I couldn't measure both your position and velocity with more precision than this h bar, but on our scale, this h bar is so small that virtually we can know exactly our position and velocity. So as we said, quantum mechanics is only important in this small scale. So at our scale, we basically don't notice this uncertainty principle. And that's only when you try to deal with electrons that you have this weird thing happen and that they behave like waves and so on. So that's when you get to really small stuff, you need quantum mechanics. And this really small stuff are described by this h bar. On the other hand, so that's one of the regimes where you need to do some weird physics. On the other hand, we say that on a daily basis, you can basically just use Newton's theory of F is equal to mg to describe apple like falling. In particular, you don't feel the force of the apple like towards you or you towards the apple. The only thing that is dominating is the Earth with its big mass. But now if I'm talking about two very massive objects, such as the Earth and the Sun, they're both exerting this gravitational force towards each other. That's this general law of gravitation that keeps the planets into orbits. And so that is Newton's law of gravity. So for small stuff, I need quantum mechanics. For heavy stuff, I need Newton gravity. And there is a third scale of physics where I need a special theory. And that's when things go fast. So we mentioned special relativity briefly at some points. And that was basically said, and the statement was that nothing can go faster than light. And so basically, if you try to go very fast, some weird thing happens to you. And that's described within special relativity, and in particular, so that Newton's theory was not compatible with special relativity, as we would know that the sun disappears directly when it happens. But on the other hand, general relativity is compatible both with Newton gravity and with special relativity. So in the same way that we needed some extension to Newton's gravity to incorporate special relativity, and that was given by general relativity, what if we also want to look at very small stuff within general relativity? So stuff that are both heavy, compatible with special relativity, but also very small. So basically what happens in the center of the black hole, well, then I need a theory of quantum gravity. And just to be complete, there are two other corners to that cube. And say one of them is quantum field theory, which incorporates quantum mechanics in a compatible way with special relativity. And that's where the standard model of particle physics is. And that's what gives the predictions that we test at CERN with the particle collider. So we understand particle physics quite well, but that doesn't incorporate gravity. And so another way of thinking about quantum gravity is a theory of particle physics that also incorporates gravity. And a candidate for such models is given by string theory. So I'm running a bit out of time, so I won't be too long about it. But the idea is that the idea of string theory is to think of particles as not being some points, but actually some extended objects, so some strings and the strings vibrate, and depending on the vibration mode, that gives rise to different particles. And so you can recover the particles in the standard model of particles physics in QFT, but you can also describe other variation of the strings that would actually describe gravity. So in that way, string theory incorporates both quantum field theory and gravity. So it's a good model for quantum gravity. But people are sometimes a bit skeptical because of experimental evidence. So the reason for that, so the same way people were a bit skeptical about Einstein theory at first, because they were saying, oh, but on Earth, we don't see the effect. And then you needed the orbit of Mercury as a proof, and also this shift of the stars. Well, people are still waiting for this kind of proof for string theory. So mostly you just recover special general relativity, but then you could also see some tiny effects deviating from that. So in particular, with gravitational waves, for example, you could imagine seeing general relativity, but then like some small deviation from general relativity that could be a mark of string theory, but it hasn't been observed yet. But a particularity of string theory is that it lives in 10 dimensions. So a way of thinking about 10 dimensions is that 4 of them are the dimensions that you see in Einstein's equation, but then there are another 6 dimensions on top of them. So you can think of them are just some tiny dimensions attached at each point. And why does it make sense that you would have tiny dimensions but not being aware of them? Well, think of looking at some watering hose from afar. If you look at it from afar, you just see a line, basically. And that's only when you come closer that you see that there is also a circle. Or if you're a little ant walking on a straw, well, you're not aware of the other circle dimension. You just see something that's flat, and you think that you're only walking in one dimension. So in that sense, it would make sense that there are these tiny dimensions that we're not able to see. But if we were able to zoom in, maybe we would be able to detect them. But they're so tiny that it would take a lot of energy to see them. And actually, it would take so much energy that if you think of this of the particle collider in Geneva, these 27 kilometers of diameters, well, to be able to probe the energies where you would actually see these strings, you would need the same collider, but with the radius of 100 times the solar system. So that's very huge energies at which these strings appear, and in which you would see these additional dimensions. So experimentally, it seems really tricky to detect string theory, but I would argue that almost independently of experiments, it's just worth studying for his theoretical beauty. So up until like string theory, that was really mathematics helping physics. But then, like when string theory came along, the questions raised by string theory were so intricate mathematically that it actually led to some progress in mathematics. And actually, maths and string theory are really evolving together, and string theory raises question in math, and then math answers a bit of it, and then that answers more questions in string theory, that answers more questions in math. And so that's just a beautiful model, and that is just worth studying in that sense. And that's what I do during my days. So I'm happy to talk more about it, and I'll stop for now so you can maybe ask some questions. Thank you.